So on to our last and final example. Remember that we started with letting x be in W, and we showed that then x is a solution to a system of equations, x plus 2y plus 3z. But we change this to be x1 plus 2x2 plus 3x3 equals 0, and x1 plus x2 plus x3 equals 0. And we stated that x, which equals x1, x2, and x3, is a solution to this system of equations, right? So that means that we now need to solve for this set of solutions to this system of equations. And x will be in that. It is a solution to the system of equations, but we haven't shown, and we discussed this in class, that the set of solutions, or if we're a solution to the system of equations, then we're in W. So what we're first gonna do, we have two options. We could either show that a solution to this system of equations is an element of W, or what we could do is we could solve for the solution of this system of equations and show that if we're in that set of solutions, we're also in W. Highly encourage you to try and show that if we satisfy this system of equations, then we're in W. But what we're going to do together here is we're first going to solve the system of equations and then show anything in the set of solutions is also in W. So we start by considering the augmented matrix representation of our system of equations. And what I'm going to do is, here is my pivot entry. It's 1, it's in the right spot. And now I'm going to use it to eliminate the second row. So R2 minus R1, replacing R2, give, remember the first row doesn't change. And now 1, 1, 1, 0, minus 1 times 1, 2, 3, 0 is going to give minus 1, minus 2, 0, 0. So 0, minus 1, minus 2, 0. And we've zeroed out the last column. So now we go to the next row. Anything below this first row, step across. Oh, there's our non-zero entry. Well, we need to make it 1. So minus 1 times R2, replacing R2, gives us 1, 2, 3, 0, 0, 1, 2, 0. We have made it 1, check. We've put it in the right spot, check. Now we need to zero out that column. So R1 minus R2, replacing R1, gives 1, 0. And let's rewrite this. It's R1 minus 2R2. So 1, 0, minus 1, 0, 0, 1, 2, 0. And now we need to solve the system of equations. And this is in echelon form, but it's not as pretty as what we had before. We have the system x1 minus x3 equals 0, and x2 plus 2x3 equals 0. And here we have a system of equations that aren't pretty. That is to say, it's not all basic variables. We have two basic variables, here and here. And then we're going to have a free variable. So let our basic variables are x1 and x2, and our free variables are x3. Let x equaling x1, x2, x3 be a solution vector. Well, it's going to have two basic variables, x1 and x2, and a free variable, x3. We start by and we're going to let x3, and in the textbook it says just let x3 be in R, but we're going to let it equal t, which is in R. So it's just some variable in R, or some real number, because this is defined over the real numbers, t. And I guess you could say here, instead of R, you could do F for a generic field. And now that we have that t, what we're going to do is we can update x1 and x2 using our system of equations. So x1 is going to equal t, and x2 is going to equal minus 2t. Because if we take this system of equations, plug t into it and rearrange, our first equation gives us our expression for x1, and our second equation gives us our equation for x2. Now, x, which equals x1, x2, x3, equals t minus 2t t. Well, our next step for solving for x is we expand this and factor out our free variables, or our constants, our undetermined constants. In this case, it's just t. So it's t times 1 minus 2, 1, where t is some element of our field, which means it's a linear combination of the vector t. So x is in the span of, or a linear combination of the vector 1, 2, minus 1 minus 2, 1. So it's in the span of 1 minus 2, 1. And here t can be anything, so it's any linear combination of that single vector. As t can be any scalar, the set of solutions is any linear combination of the set containing the vector 1 minus 2, 1. So thus, the solution set equals the span of the set containing the vector 1 minus 2, 1. So we'd like it if we were done, because we have the set of solutions, but we're not quite done because we haven't shown, or we haven't represented W, or shown that this is a representation of W. So we need, by construction, W is a subset of the span of the set containing 1 minus 2, 1. Well, we need to show that the span of the set containing the vector 1 minus 2, 1 is a subset of W. So let x be in the span of the set containing 1 minus 2, 1. Then x equals t 1 minus 2, 1, where t is in R, which implies that x equals t minus 2t t. Well, note that, not wote, note that t plus 2 times minus 2t plus 3 times t equals 0t, which equals 0. And t plus negative 2t plus t equals 0t, which also equals 0. Therefore, x is in W. Thus, W equals the span of the set containing the single vector 1 minus 2. And we've concluded the question.